Hey there. A few weeks ago, maybe a month or so ago, I received a question on what's called the Bachelier model, or at least that's how I assume it's pronounced. It's a French name. It's an option pricing model from the turn of the last century, around 1900. And there's been some renewed interest in it because, as you may have recalled, earlier this year, 2020, March or April, there was actually a negative print in the oil futures. And trading firms and risk management firms and whatnot did not have the capability to really handle negative commodity prices in their risk assessment models. And recently, the CME, the Chicago Mercantile Exchange, has announced that it is going to use this Bachelier model for future risk management type of things. So someone asked if I could do a video on this, and I kind of have mixed feelings on it because while I am an options trader and have traded options for like a decade and stocks since the 1990s, I'm really not an expert on financial mathematics. And there are things online, including YouTube, that go over this model and its derivation. So rather than reinventing the wheel and doing something where I may not be familiar with some sort of nuance of how this works, I think what I'm going to do is basically just show the equation, do some simple calculations with it, show how it compares to the Black-Scholes model, show how you calculate, numerically at least, calculate the associated Greeks with it, delta, vega, and then if there's time, maybe show how to modify our implied volatility code to use this model instead of Black-Scholes. And again, depending on time, we may fire up SymPy, we may import the SymPy module and do some of these calculations analytically because I'm really too lazy to calculate the derivative of these huge functions by hand because, well, you've seen how many typos I make. You can imagine how many mistakes I'd make calculating a derivative where it's chain rule inside a chain rule inside a chain rule. So yeah, what I'm going to do is when I clean up the notebook, I'm going to put in the links I used to get the equations for this model, and a link to a paper on comparison between it and the Black-Scholes model because they're similar and different in many ways. The main difference between these two is that Bachelier assumes that prices are normally distributed, whereas Black-Scholes assumes that the instantaneous returns are normally distributed, and that allows for things like negative prices in Bachelier, but the normally distributed returns basically gives you a log normally distributed prices, which prevents prices below zero. Okay, so let's just jump into a notebook and get started. Okay, notebook. All we really need are NumPy and the SciPy stats because we're going to need the normal distribution function. And I've also imported matplotlib. And if we do some symbolic stuff, I want to pull in some stuff from SymPy, and then this is just stuff to print out SymPy in a nice, pretty way on the screen. So I've also pulled in some of our Black-Scholes stuff from the implied volatility talks. So here's the Black-Scholes formula for the price of a call and put, and we're just going to concern ourselves now with calls. And here are the definition of D1 and D2 that go as inputs to these distribution functions. And I've also copied in those actual coded up functions here. So call price, put price, the objective functions for finding the implied volatility. And if you recall, we need to calculate the derivative of those prices with respect to volatility, which is vega. So here's a function to do that. And that's about it for this. Remember, this is Black-Scholes. So for the Bachelier model, here's the price of the call, and it looks very similar in many ways to the Black-Scholes model. And remember that this phi here, this capital phi, is the cumulative distribution function for the normal distribution, and so that shows up here. And likewise, this lowercase phi is the density function, again, for the normal distribution. So what I'm going to do is just define some basic a range of stock prices or whatever, and I'm going to plot out this Black-Scholes function of a call as a function of, I'm going to choose stock price, and then we're just going to compare it to this Bachelier model. So let's start just by coding this up, and through the magic of editing, here we are. So we have a function that returns the Bachelier price of a call. Run that. So what I'm going to do is say our time to expiration is going to be 30 days. And remember, this needs to be in years, so it's 30 divided by 365. our implied volatility sigma. Now this is where we're going to differ a little. This is the implied volatility for the Black Scholes model, which is based on normally distributed returns. So this is going to be equal to 30%. Our strike price we typically take to be like 105. Our risk-free rate is 0.01 or 1%. Again, that's annualized. And for stock price, we're going to use a range of prices, and let's just go from linearly spaced from say 90 to 110. I don't know how many points we want. 100? 100 points should be enough. Something's wrong. So what happened? That should be a comma. Okay, so let's just run this through our Black Scholes model. Let's call the call price, we'll call it BS for Black Scholes. Call price, sigma, S, K, R, and T. Okay, and let's plot that out. plt.plot S, comma, C underscore BS. Let's make that a line. Black line, and we will put a legend on here just to keep our plots separate. Label is equal to Black Scholes. plt.grid true. plt.legend. Oh, you know what happened is this function actually returns those D1 and D2 values. So let's just go here, D1, D2. That should fix it. And there's our Black Scholes price as a function of stock price. So let's come up here and we'll just copy this and do basically the same thing for the a Bacheleier model. So paste, let's make this BA instead of BS. We only need one D for this. The function name is Bacheleier. And we have to modify our sigma, because remember this is the sigma for the Black Scholes model, and we need to scale it to the Bacheleier. So I'm just going to multiply it by the price. So looks good. Does it run? Seems to run. Let's just plot it, and we'll do the same thing. We'll just copy. Paste it in. This is going to be Bacheleier. And let's make it, I don't know, let's make it blue dots. So there we go. They're damn close. Not perfect agreement, but pretty close. And that's basically the idea. You're going to have the same, very similar results unless you really crank up something to kind of an extreme level. So let's, for the time being, we'll get rid of this in a moment. We'll copy this, paste it down here. Rather than having a constant sigma here, let's go, we'll do an at the money call. So we'll set the stock price equal to 105, same as our strike price. Let's have a range of implied volatilities. So sigma is equal to np.lin space. Let's go, I don't know, some small number like 1%. Up to 100%, and we'll take 200 points, and let's just plot out. Let's calculate the call prices, and then plot them out again, just as we did up here. So I'm just going to borrow this code here, paste it in. Does it run? Yes, it does. And copy. Paste, and we need to change these to sigma. Looks like I'm missing a comma. Where am I missing a comma? Here. So again, we have pretty good overlap. Let's go up to 500% implied volatility. There you can see they're starting to diverge. Let's go to 1,000%. Here we are. Even more divergence. Let's go ridiculous and go to 10,000%. So you see the Black Scholes basically plateaus at a constant price, whereas the Bacheleier just keeps increasing linearly. So as long as you're kind of in the normal range, you're going to get relatively decent agreement between the two models, but they do differ in some respects. So I'm not going to keep this cell, just delete it. And now let's just go on and play around with this numerically. Recall that the delta from the Black Scholes model is basically this D1 value run through the distribution function. So let's go, let's call it capital delta underscore BS is equal to norm.pdf, CDF of D1. Let's just rerun this so that we're dealing with, actually, let's not do that. Let us grab this here, because we just want, again, a fixed stock price. So what I'm going to do is come down here and set the stock price. I don't know. Let's go ahead and again at the money. So 105. So here's our delta. Let's print this out. Print delta BS is equal to delta underscore BS. It should be about 50. And indeed it is 52. So we could actually take the derivative of this by hand and work out a formula just like we do, like we have for the Black Scholes, but I don't know about you, but I don't really feel like calculating the derivatives of something like this by hand. So we can estimate it numerically. And we see since these plots overlap, we should get pretty much the same result, 52, 50, 51, 52, 53, in that range. So let me get rid of this. I'm going to cut it out and paste it in down here. And we're just going to do a very simple rise over run formula. We're going to look at the change in price over almost an infinitesimally small change in stock price. So our epsilon, which will be our change in stock price, epsilon is, I don't know, let's 10 to the minus 6. And so let's come down here and we'll make this, I don't know, C1. What happened? Here we are. E. That kind of makes a difference. And we'll take another price, we'll call it C2, and we'll just bump up this stock price by epsilon. And I'm not going to bother changing this price here. It won't make that much of a difference. So C1, C2. So our delta underscore BA is just going to be C2 BA minus C1 BA divided by epsilon. So let's print this out and see what we got. Delta BA is equal to yeah, 50 delta. So not surprising, they're about the same since the plots are about the same, the slope of these curves are about the same. Okay, so I have copied and pasted our Newton's method code from the implied volatility videos a few months ago, and you remember we wrote this in a kind of a generic way where we pass in a function and its derivative, and it spits out the root of that function f. So what I want to do is kind of use what we kind of worked on up here, where we calculate a delta with some sort of numerical approximation, and let's see if we can calculate the implied volatility. So what I want to do is see if I can recover this call price where we calculated the delta. So say C1 here. If I take that as our given call price, I should be able to recover the volatility, which we assumed, which was 0.3 times the stock price of, what was it here, 105. So let's see if we could reproduce that with our Newton's method code. So if you recall, implied volatility, solving for the implied volatility is a root finding problem, since we can't We can't rearrange these equations algebraically just to get to the numbers we want, but we can do a numerical root finding process. So we already have the well, we actually don't have this function. Our function is going to be the Bacheleier call price C1 minus whatever the model is predicting, given some arbitrary implied volatility. And we want to find the volatility that sets that equal to 0. So that'll be our objective function. So we need to write that. And we need to write this derivative function, which will give us essentially vega for this type of model. So it's the derivative of the call price with respect to sigma. So let's come down here and code up our objective function and our vega function. So what we will do is we will basically borrow from some of the stuff we've done up here. Let's see, call objective function. So this is basically what we want. We want to copy something like this. So copy. Let's just run this. Let's just paste that in. And we will call this call underscore BA objective function. And it's the same idea, except we're not doing the call price. We are doing Bacheleier. Yeah, and the price we pass in is basically going to be the number we calculated up here, just to see if we can recover the same sort of numbers. So I'm probably making a mistake here, but I don't see anything as of now. So let's just run this. Okay, and now let's write our calculate vega. Def calculate vega BA. That's going to take an argument sigma and additional parameters, which we called args. And the signature is basically the same as here, so it's the same structure as up here. So just as before, we're going to define an epsilon is equal to 10 to the minus 6. Let us calculate a call price C1. That's equal to sigma SKRT. Let's calculate a C2. Oh, we're going to need the D here, are we not? Oh, C1D, and I forgot the actual function name. There we go. So C2 comma D is equal to Bacheleier. Sigma S plus epsilon K, R, and T. So let's see. Let's now just return C2 minus C1 divided by epsilon. Okay, we should be good to go now. So let's come down here. Actually, let's figure out what this call price is up here, which we print C1. So this is going to be our call price. So let's just copy that. We will come down here and say our call price, we'll call it C0 is equal to this. Our stock price is 105. Strike price is 105. R is 1%. And T is 30 over 365. So args is going to be equal to, what's the format again? It's SKRT and the price. So let's come back down here. S comma K comma R comma T and C0. Looks good. What does our Newton's method excuse me take? Not that much. So we should be able to just call it and it returns a whole bunch of stuff which we really don't need. So paste is equal to Newton's method, call objective function. Let's just make sure this is correct. I need a BA here. Our derivative is calculate, what's wrong? Calculate vega BA. And let's take an initial guess. Come on, where's my mouse? Let's take an initial guess of our root of, I don't know, 50%. So anyone want to take bets on whether this runs? What happened? We did not get our R here. Okay, so I made a couple changes off of the recording. In my vega function, I had originally tweaked this S, but we want to tweak the sigma. So I moved the epsilon from here to here. And the other change I made was in our function to calculate the call price. It returned a tuple. It returned the call price plus that D value. I don't need that D value for the Newton's method thing. It screws up the code because it assumes it just returns a number. So I got rid of that. I'll clean up the code later and then put that back in somehow so that the rest of the code runs, because right now we probably break a bunch of other things. So that seems to be good. Let me come down here and rerun this. It seems to run. So let's print out, come on, the root of that function, which is our implied volatility. It is 31 essentially. But to put it in Black Scholes terms, we need to divide it by the stock price, so capital S. And we're back to 0.3, which is exactly what we suspected. So I'm going to call it quits here and clean up this notebook, and then maybe do a little companion video on playing around with this with SymPy, so you can get actual analytical expressions for like the derivatives and the equivalent to Greeks. So right now the computer is kind of misbehaving itself, so I'm going to end it here and do that in a follow-on video. So rather than recording a separate outro, I will just say here, see ya.